Now that we've discussed uncertainties and confidence intervals, we have to move on to linear calibration. So the first thing is, why do we need to calibrate an instrument? Well, we calibrate an instrument by applying different inputs and determining how the output of the instrument is related to the inputs provided. So while the uncertainty in an output of the example load cell is important, it's not the end goal. We want to determine how the output changes as we change the load that's applied to that load cell or any transducer. So ultimately we want to determine a mathematical relationship to allow us to estimate what the input is. That is, we want to figure out if we measure the output voltage, how much input load was applied to the load cell. And we also want to now move on to including uncertainty in this estimate. All right, so how we apply or how we obtain a calibration is by applying different standards as the inputs. All right, so for the load cell, this means that we're going to apply different known loads. Ideally, we'd do this in a randomized order, and we would record the output. So for the load cell, we're going to hang different weights from the load cell and record the voltage output of that load cell. But in general, any transducer, we're going to look at the relationship between the output and the applied standard input. All right, so then we're going to plot the output to verify that a linear relationship exists, and if a linear relationship does not exist, we cannot apply a linear regression. We'll have to do some other fitting, and we'll talk more about how to do nonlinear fitting later on in the class. Okay, if a linear relationship exists, we're going to compute the best fit line, and we can do this using Excel or other software packages. We can graph the trend line, or we can use the slope and intercept functions, which we will cover. But first, we need to talk about how this trend line is created and what these things mean. Okay, so a trend line is created in the following way. If we have a bunch of observations, so if we apply a bunch of different loads and we measure the output voltage, we can plot the output voltage as a function of the applied load. Okay, and we can attempt to draw a line between those data points. And the goal here is that what we want to do is we want to minimize what's called the residual. Okay, so we can draw this line, and then what we're going to do is for each point, each data point that we've measured, we're going to measure the distance, the vertical distance, in the y direction from that point to the line that we've attempted to draw through all of the data points. Okay, and the residual for an individual point is the difference between the point and what that line would tell us for that given input. So here, x is our input load, and y is our output voltage. Okay, so we have a trend line with a slope and an intercept, m and b, and we say, all right, at 15 pounds load, we have this data point right here, which is y sub I. All right, but our trend line tells us, the mx plus b tells us that we should get something slightly higher than what we actually measured. And that's the residual. Okay, so we're going to take all of the residuals for all of the points. And the goal in coming up with a line of best fit is that we want to minimize all of those residuals. We want to get adjust the slope and the intercept of this trend line so that we minimize the residuals for all of the points. Right? So what we want to do is, our goal is to minimize the squared residuals. Okay, so what we want to do is select the slope and intercept value to minimize the difference between all of the points and the trend line that we've tried to draw. Okay, so again, what we want to do is take all of those residual values, the difference between the observed values and the trend line that we have tried to draw, and we want to change the m here and the b so that we can minimize, make the sum of all of those residuals as small as possible. And for a straight line, it's easy to come up with this value. This occurs when this is true. So when we take the difference between the individual input, x, and the individual output, y, and we take the product of each of those individual points, and subtract the mean from the x and the y and multiply those together. We add all of those up and then divide by the squared difference between all of the input values. And we sum all of those up, take the quotient of the two of them. That provides our best fit, our best fit slope, which minimizes the squared residuals. And then we can find our intercept by taking the average output value, the average y value, and the average input value, and rearranging the line equation and using our defined slope here. Okay, so all that is some math behind it, but that's basically what Excel or MATLAB is doing when it is coming up with the best fit line to linear information. Okay, now of course if we repeated this calibration a bunch of times, let's say we collected calibration data for 3 different trials. Trial 1, Trial 2, and Trial 3. Now, Trial 1 corresponds to the data points in black, Trial 2 is gray, and Trial 3 are the red data points. You can see that each time we repeat this calibration, we'll come up with a slightly different result. We'll get different uncertainties or different noise coming into our measurements, which is going to cause, when we try to draw a trend line through all of the data points, it's going to cause the linear trends to be slightly different from each other. They're going to have a slightly different slope and a slightly different offset. Okay, so obviously, if we take real data, we're going to have some uncertainty in this best fit line. So the best way to come up with a best fit linear calibration is to use all of the replicate trials, use all of the data that we have available to us. So instead of trying to come up with multiple individual linear fits and doing some averaging or something like that, we want to use all of these trials together. So we're going to combine all of the trial information together and come up with the best fit line that way, using all of the individual points. Okay? Now, to quantify the uncertainty that exists in this best fit line, we use something called the standard error. All right? And the standard error of the regression line is denoted by this S with a y/x. Subscript. And what that indicates is that this is similar to our estimate of the standard deviation about the line. Now notice that this is calculated slightly differently from how we actually calculate the standard deviation of a set of data points for a single input. All right, so it's different than if we just applied a 25-pound load and looked at the variation in that. What we're looking at or trying to quantify is the variation in the data about this best fit line. Okay, we can use this function STEYX, the standard error in a linear calibration function in Excel, to calculate this for us. So no need to memorize this formula. We can find how to do this in Excel as well as MATLAB. Okay, something that you're probably familiar with from Excel is seeing this r² value, and the r² value provides an indicator of how well the model predicts the data, but it is not a statement of the standard error, or it's not a quantification of how much error exists between the or uncertainty exists between the best fit line and the data points. Okay, so even though it tells us how well things fit, it doesn't tell us anything about what the variation is in the output voltage about the best fit line. Okay, so now what we're going to do is we can take the slope and the intercept, and we can calculate the standard uncertainty in the slope and the standard uncertainty in the intercept if we calculate the standard uncertainty in the best fit line. You'll notice that the standard uncertainty in the best fit line shows up in both of these equations. Okay, and the uncertainty in the slope is calculated by the formula you see here, where we're going to take the standard uncertainty, divide by the sum of the square differences between all of the inputs and the average input, which is x bar. And the standard uncertainty in the intercept is slightly more complicated. All right. Now, to obtain confidence intervals, remember that this is the standard uncertainty. This is analogous to the 68% or one standard deviation, but it doesn't tell us anything about 90% confidence intervals or 95% confidence intervals. So we're going to apply the same logic that we have in the past with the single input value, the multiple replicates of single standard inputs. And what we're going to do for our best fit line is we can use the standard uncertainty and multiply it by the critical t value. Now, with we have to use 2 degrees of freedom, and we'll talk about that. Okay, so basically what we're going to do is we're going to determine the uncertainty in predicting the output of our load cell or of our transducer. Now remember, for our load cell, the output is the voltage and the input is the load. Okay, so using the standard error of the regression line, we can estimate the output given any input within some confidence interval. Okay, so here is our best fit line. This is our this is the output. All right, here's the best fit line, the slope and the intercept for some given input x value or our load value. And then to come up with the confidence interval on that output, we're going to have to calculate a student's t critical value at some given confidence or alpha level and some number of degrees of freedom. We're going to have to calculate, or we will have already calculated, the standard error in the regression line. And then we're going to have to multiply the product of those two by what's under the square root right here. Okay, and what's under the square root right here is 1 over k. So k represents the number of samples to be taken and averaged when making subsequent measurement. So this would be if I make one measurement and want to know what the confidence interval or the limit, the confidence limit is with a single measurement, this value would be 1. If I take a bunch of measurements and average them together, this would be the number of measurements that I've used to average together. Okay. 1 over n represents the number of samples that were used to create the best fit line. So this is how many data points were used to come up with the estimate of the slope and the estimate of the intercept for the best fit line. Okay, and then we have this other term right here, which is we're going to take the squared difference between all of the input values and the average input value, and we're going to also divide that by the sum, or sorry, we're going to take the predicted, we're going to take the input value for which we would like to predict the output. So we're going to take the load for which we would like to predict the voltage output for the load cell, and subtract from that the average of all of the inputs that were used to come up with the calibration line, square it, and then divide by the squared deviation in the x direction or of all of the inputs. So we're going to take all of the input values subtract that were used to come up with the calibration line, subtract from that the average of all of the inputs that were used, square them, and add them all up. Okay, so to come up with the t critical value for the student's t, we're going to use n minus 2 degrees of freedom. Okay, so this is slightly different from what we did when we had a single input, a constant input, when we were looking at the variation in a constant input value. Here we have 2 degrees of freedom, n minus 2 degrees of freedom to worry about. So if we used 30 samples to come up with our best fit line, we would come up with the student's t critical value by looking at the chart and using 28 degrees of freedom instead of 29 or 30. Okay, we'll go through an example of this, but what does the output prediction interval tell us? Well, with one measurement and 90% confidence, basically what we can do is we can take all of those values that we had before and our best fit line, and then we can append on either side of that these lines, these gray lines that represent the 90% confidence interval. Okay, so basically we can say that if we apply a load of 15 pounds, we can predict that the output is going to, we can draw a line, project lines over to the y-axis here, and we'll have two bands, and we can predict that the output is going to be somewhere between 0.4 volts and 0.7 volts approximately, 90% of the time when we apply 15 pounds of load. Again, if we come up here to 20 pounds load, we can say that the output voltage is going to lie somewhere between about 0.6 volts and a little over 0.8 volts with 90% confidence anytime we apply a load of 20 pounds force. Okay, but the purpose of this calibration is not to predict the output based on the input. In other words, if we apply 20 pounds load to the load cell, we know that we're applying 20 pounds load. And we don't really want to predict what the output voltage is. It's more likely that what we would like to do is measure the output voltage and predict what the applied load into the system was. So basically we want to work the system backwards. If I get a reading of 0.6 volts of output, I would like to predict how much to try to predict how much load was applied to that load cell. I would move over here and I would see that there's a wide range of values somewhere between about 15 and 20 pounds force that corresponds to an output of 0.6. Okay? So how do we do this? How do we actually compute this? Well, basically what we're doing is we're rearranging the best fit line. We're going to, instead of predict the output y based on some input x, what we're going to do is rearrange the equation so that we're predicting x, our input, based on our output and our best fit calibration parameters m and b. Okay, and now to predict the uncertainty in predicting the output based on this rearranged calibration line, we're going to have our standard uncertainty. We're going to take our standard uncertainty in the calibration line, divide that by the slope, and then again multiply it by this radical. All right, and again, n here is the number of samples that were used to create the best fit line. K tells us about the number of samples of the output that are to be averaged to predict the input value. All right. Of course, remember that S stands for our standard uncertainty. So this will be the standard uncertainty in predicting the input, the voltage, predicting the load of the load that's applied to the load cell by reading the output voltage. Now this is standard uncertainty, which corresponds to approximately 1 standard deviation or encompasses about 68% confidence interval. If we want to adjust that to some different confidence interval, again what we need to do is use the student's t value with n minus 2 degrees of freedom, where n again represents the number of samples that were used to create the regression line, or the best fit line. And we can now, using the calibration and statistics, determine the most likely input, again, what is the load, and what is the confidence interval on that load when we have some transducer output. And to do that, we're going to take that critical t value with our confidence level, alpha, and our degrees of freedom, which is n minus 2, multiply that by the standard uncertainty in the input prediction. Okay, so that's how we're going to do it, and we're going to go through an example in a future video to kind of show you how all of this is done in practice.